Hello. Hello, 1 2 3 1 2 3. Hello. Hello, 1 2 3 1 2 3. Hello. Hello, 1 2 3 1 2 3. Hello. Hello. So today is the second day of me building my own CPU emulator from scratch with C. And yesterday we left off. Uh, so yesterday we were in the just what I say. So we did this stuff like we created a memory setup. We had two functions to write and read to memory, and like one to fetch the current CPU instruction, and then the next CPU instruction. And we had a main loop with the main CPU cycle going on. And this code had some issues, and I checked it multiple times yesterday after the stream ended. So I'm gonna fix those issues and make this part better, make the full code better, and like also some like formatting issues. I'll fix those. Add some more comments, as some people suggested that I should add more comments. So yeah, I'll do that today. And it's just first I'll add git ignore file. Git ignore. I'll put main binary here. Anything like dot pin, also as dot o occupies. So CPU now make, and so format this part of the code so that it looks nice. Am I using this library? Yeah, no, I'm not using this library. So why did I put it here? Um, this library. So why did I So far 0 people is watching now. So I'll quickly start with the issues. So first of all, uh, I think I have messed up with the memory allocation part because right now, so what calloc actually does is calloc. So we can see the documentation from calloc example. So here it says the size t count. I didn't like I misunderstood what count exactly means, and I think so. Allocate memory for 5 integers and initialize to 0. Okay, so here I'm doing the same actually. Just memory size. FFFF. We don't need the word. We don't need that, and also we are not doing any memory after memory allocation. If there is a fail, we are not doing that. Check also. So if mem is equal to null, then bring memory allocation fail return one. Also, so we don't need divided by 8 because here I get it, I got it totally wrong. So here count is the memory size, and this is the like size of the unit, every unit. So I got it wrong. I definitely got it wrong, so I'm gonna fix it. And also Our issue was this equals to if you the hex calculator. I don't have hex to decimal, and if we check the value, it is 35, but uh, what 64 KB the byte is, it is kilobytes. 64 KB. Okay, that is so it should have been something like 0000. Yeah, this is the pro right value. So I have to make it 0x1000. How many zeros for 10,000? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. And after that, we have um, so we did something else. So there is another issue, which is uh, basically we are hard coding the value here, but PC value program counter after reset. So after reset, the program counter goes to mm, so after every reset, this is reset system reset. The program counter goes to FFFC. Okay, points to FFFC memory location, and we're like hard coding it, but it shouldn't be like that. We need to read it from the memory, right? So the problem is we are the pointing it directly to FFFC, but instead of pointing it to FFFC, we need to put the values of FFFC inside here. So we have to do something like, so we need to read 2 bytes because the PC is so it is 16-bit, so 2 bytes basically. So we're gonna read 2 bytes. And the first byte is the low byte because it's little endian. So low byte is read mem. Fast. We need to also pass the menu. memory and the address is CPU. FC D uh, I byte. And now we do a calculation. It is called so now we have to convert the little Indian to uh, little Indian value to um, so how we did do that is, so our memory reads something from here, right? So we are reading from FFFC and FFFT. So FFFC goes first because it's little Indian 0, 1. Then it goes 0x00. So it's reversed. This is the low bit, and this is the high bit. Okay. And we have to reverse it. To reverse it, we can do something like, first we have to do high bit and do something like high bit in CPU and low bit. So here, what we are doing is we are moving the high bit, we're shifting the bits of the high bit to 8 byte left. Uh, then we are like doing an OR, and it is making like combining them both. Uh, right. I think it would be better if I can visualize it. Yes. It should visualize online. 0x. So we're first doing 0x. For example, if we do something like 0x 1, 2, 3 numbers bit to shift, we're doing left shift. So hexadecimal number. So you see it shifted to towards the left. Then we have to add the value, but there is no way we can add it here. So where can I put the value? It is going to take 32 bit meter. So essentially what it is doing is, first we have the high bit. High bit is 8 zeros basically because it is 0, 1, 2, 3, 4, 5, 6, 7, 8. Then we are saying to shift the bit to 8 positions. Then it is becoming something like 1, 2, 3, 4, 5, 6, 7, 8. Now we are just ORing them both. So what is happening is this is coming in like zero. So we are merging them both. Think about it like this. 1, 0, so 0, 1. Then 1 at the end, it's 1. We can do it something like, we also can do something like, for example, if the low bit is 0x, 3 3, and the high bit is 0x44. Okay, so this is the low bit and this is the high bit. So if we go and in Python and do something like 0x, so low bit, high bit is 44, 44, 33. The value is something like this, right? If we do the same here, so the bit shifting part here, we are first doing the 8 positional shifts. No, then we are ordering them both. So then we have 0x33. You see, we get the same answer. So I hope it makes sense. I don't know if I were able to explain it properly. So no one is watching anyway. So here we do like high, a bit shift, and all low. Expected. Yeah. Okay. Talking. Increase memory conversion in total. We make it bigger. Mm, how can we do that? Is to do. Now there will not be any issues. Yeah. We can bring people log CPU inside long block. We can need block value block parameters into CPU, aka CPUs. the so clock 0, we have PC value to 0 x. So 0, AC is 0, everything is 0, y shouldn't happen. We have LDA. Correct position. So let's send it to somewhere else. LBA. At that position, we can do DA 0x42, and we have no we run it again. Yeah. So currently CPU is reading. So this is our memory layout for now. So this is the reset vector. Then we have our program. Yay, we have our little program and our CPU. And in our program, what we are saying is, in this address, in this memory address, we have a load operation. Then LDA basically loads anything. LDA instruction basically loads anything into register A. LD load A, register A, and it loads the next byte into memory. And the next byte is this 42. Then we have a no op operation, and it just stays there. So after that, we have just no ops. The PC is this, and no op operation. Accumulator, yeah, all the accumulator always stays like this. Then we can do something like also, we can give it another value. Then we can say, okay, at this position and this position, the value is 1, and it stays like that. This shouldn't happen. 2, 4, 3, LDA. Okay, why this is not working? So this part should also do the same, but it is not doing the same. It's going into this part, but then it's not changing the load value. It's not loading this. Why is doing this? Just just 1 second. I have to answer some messages. Someone commented, thank you. Hello. So, so right now our program, this is our program, and we have just like two instructions, load operation and no op. No op basically does nothing, and load basically loads one value, next value into the accumulator register. So LDA, load into accumulator, and it loads it immediately. We have the logic in here. Also, we wrote some custom program for us. Seems like, so this expected result is it will load first. It will go here. The memory will period, and the CPU will see, okay, load the next address mm, value to the accumulator register, and then move on to the next part. But it's not doing that. The accumulator is staying like this. If we look into the load register, what else it is doing? Okay, thank you for uh, commenting. Thanks a lot. So we need to trace this issue. we would know what will happen. Um, Goes there, it reads it, stays the same. Accumulator gets data. Then we have the next stage. Next step. When we take a step, upload has fetch byte. So fetch byte is doing this. When a byte is fetched, the PC counter goes up, right? I think let's add a print. So I am still confused why it is happening. Let's see. Let's try it again. So we have scroll counter going one up. PC values like 0, 2, 3. We also need AC. AC value is CPU AC. Okay. First, the AC is 0 when it goes here. Then the AC, then here is the load operation. Then we have the load happening here. Then we have another. But here, from here, fourth instruction, like fourth position of PC should change the AC value, but it is not doing that. So Let's see what are the opcodes. Code is T T X opcode EA 41. Then 41 is 41. Word is 41. So position. Okay. Okay. So issue was fixed. Yeah. So the issue was the CPU worked perfectly fine. But the issue was I wrote wrong code. I was the issue actually. It was my skill issue actually. 42, then 41, 41, 41. We can do something like also. Uh, so we had a no op. We can do something like 4. Then we have 5. We have 6. We have 7. Again, is not working. 4, 5, 6, 7. Why? No op. Then LDA. Oh, because I'm not changing the value here. Yeah, it is working right now. Fine. So we have a working CPU. Let me add some more comments. I think that will make more sense. So here I'm checking for this stuff is pretty obvious. I don't want to clutter the so we set up new read the next step. Okay, I think I haven't shared the link to my Discord server. I'll share that. Yeah, I think I have added to sparks and it is good enough for me right now. I will push it to get me uh, added. So what I did is I uh, fixed some bugs, fixed bugs, typical Git commit message, very typical. I, and it's true. I fixed some bugs, right? So I'm not technically lying anywhere. So now I will be implementing a jump to new location about, mm, instruction. I will just call it GMP jump as the instruction, and it will immediately jump to the uh, new position, and how it is done. Jump to new operand, first byte PCL. I have to be okay. These are the CPU steps, and I have to like work with the CPU step. I think I should get down and like start implementing the CPU step. Uh, I will, but not now. Not now. Operand first byte PCL, operand second byte PCH. Okay. So three cycles. Okay. Um, direct. So, mm, I'm going to jump like absolute jump. We are gonna do the absolute jump first, then move on to the next, I guess. So what it does is it fetches opcode. First, we have to see this. We will fetch opcode. Then uh, we will like fetch the low byte and the high byte definitely from the addresses. So I think first make a fetch word, u uint 16 fetch word, and we need to use CPU asterisk CPU. Then we have memory UI and memory. Then we will use uh, UI is 8 below. First, low byte definitely fetch word. Fetch byte CPU. Then we have high byte. Then we return the value definitely. Return. So you say, so we did it previously. We're just converting like the little Indian 2 bytes into one like, normal hexadecimal or like, decimal value. So this is the high byte. High byte goes first, then the low byte goes second, and we're just adding them. We're moving it 8-bit forward. Simple, nothing else. And then we are just combining. Then the rest of the 8-bit is zeros. So when we add them, they become merged to one value. So we did that, and now we have to like we fetch the step function already fetches the opcode. Then we do our word fetch word. Now word returns the next value. Uh, Here we will have case JMP jump and wait at the end and uh, ADDR next address definitely fetch word. Okay. Jump has output for jump, absolute jump is 4C. 4C. So we also need to like so I'm not putting much effort maintaining the code structure. I think after I implement the jump, then we have to do two things. First, it is becoming very necessary. First, we have to write a method or a constant method so that we can, not method actually function, so that we can dump the memory into a file, and we can load the memory from a file instead of writing directly using something like this, a function. It looks ugly and it is pretty weird. Or we can use a compiler or something like that. Let's see. And also we have to maintain the code structure properly, because as the code is getting bigger, it is already 150 lines almost. So as it is going bigger, we have to too many arguments. Yeah, I know. CPU, and we have the memory. So after that, if we to PC value to new address. Um, anyone watching right now? Yeah, no one. Today I'll stream for another hour and a half, I guess. Yesterday I streamed for around 3 hours. I think that's too much. I think, yeah. So now we have a jump operation. So we can write a piece of code. So we can update our code to implement that. So we load, and so jump will, yeah. Zero x 8 0. So the low byte goes first. We're going to jump to 0 0 here. We're implementing a loop, nothing else. So this is our memory to this is our memory address. 0 let's see. We're essentially saying, okay, jump to here. Let's see. Yes, we're jumping back. Yeah, we implemented our CPU, and we have now jump operation. We have three operation functional and running. Yay. We have, so we have jump now. Now our code jumps to the address, and it keeps looping and looping. If we like continue with what will happen, let's see. If we just, it will go forever. It will just go forever and loop and loop and loop and loop. Will not do anything, nothing else. So we have a jump essentially. We have a jump and we have a load operation, jump operation. We have uh, jump to new location saving return address. Okay. Do we want that now? Takes 5 operations to indirect jump. Okay. What is indirect jump? 3 bytes, 5 cycles. 5 cycles. Jump indirect. 65 to jump in wait, indirect indicates to load 16 bytes from a specific memory location and jumps to it. Okay, it jumps only. It is only those instructions according to direction. The instruction uses the junction as is stored in and row by and by. Interesting. So next, what should I do? Oh, I should. Uh, I should implement now the memory location memory load part, I guess, because I don't want to write it like this. First, I should create some header files and put them the other functions here. I think I will do that first. The memory util hills dot c. To be in. This function is kind of useless. I need to update it differently. Not now, I guess. Um, add CPU util dot c e e use of undeclared identifier. So for now, I think I'll move the memory setup memory to main.c for now. Not too long. No, it's not. Make uh, it's is working. So I restructured the code a bit. I think I should write a README file also. README.md. Uh, I don't know what should I write. I'll write it some times later, I guess. Hmm. So jump in direct has recently I have been developing an emulator for. Okay. Oh, I can just copy it from here. Everything. He wrote it in C sharp. Damn. I'm writing it from C. Okay. Oh, he structured the code in nice manner. He put the CPU stuff there in one place. Nice. Yeah, if I were to do it in Python or Go, or like if I had the opportunity, or not opportunity, if I had decided to do it in uh, C++ or object-oriented language, or Java, or JavaScript, or Python, then a lot of stuff would have been easier, I guess, because then I didn't have to. Like, I could have made a class, CPU class, then memory class, then yeah. So nice. So what did he do? Recently, I've been developing an emulator for MOS, this CPU, an 8-bit microprocessor used for many famous systems such as Apple II, Commodore, PET, and Nintendo NES. Uh, what does NES mean? Nintendo NES. Nintendo Entertainment System. What is PET? PET. Personal electronic trans transact trans interesting. Exactly. Nice. While implementing the jump in direct instructions, some but not all of the instructions in the step test would fail. My bug logs revealed that the culprit was the high order byte of 16-bit program counter. The high order byte. Okay. High order, yeah. Which was always being set to 0 as opposed to the expected value 98 in this case. Okay, the registers A register, accumulator X, Y, S, state, uh, P, E, C, so A, C. Actual resistors. Uh, then it takes you to another location totally. Expected memory, uh, actual memory is everything is same. Apple 98. Okay. PC benchmarks. Okay, not just PC benchmark. This part. The high rate is looking missing actually. Okay. After some investigation, I discovered that there's a bug in the original 6502 hardware that occurs when a page boundary is crossed in jump indirect instruction. According to there's no carry associated. Mm, just which is a first bind, which one is the output for jump and the Interesting. Nice. Uh, brings the to go. Now I think I have to implement. I will implement memory dump and memory read thing. So should I do it in C? Yeah, I should do it in C. So uh, oh, I will take a break for some time because I have been streaming for almost 1.5 hours, and I'll continue the stream today later, a little bit later, I guess. And yeah, thank you all for watching. Just one person is watching, whatever. Uh, Feel free to join our Discord. We have around 1,500 members. Have a good day. See you soon.